Bismillahirrahmanirrahim. Students, our today's topic of discussion is semiconductor. From your previous classes, you all know somehow about these semiconducting materials. So we start with their introduction. First of all, we will discuss what are semiconducting materials, and then we go about their classification, that how semiconducting material can be classified. So to understand that what are semiconductors, so if we focus on the last topic of our previous chapter, in which we study about the band theory of solid, there we classify material into three categories. The one in which valence and conduction bands overlap with each other, they are called conductors. And the others are in which valence and conduction band has a very wide band gap, so that electron cannot jump from valence to conduction band. So there is no conduction. So those materials are called insulators. So we also discuss a class of material which lies in between conductor and insulator. Their properties are in between. They are neither good conductor, they are nor good insulators. So such materials are called semiconductors. So semiconductors have electrical conductivity between metallic conductors and insulators. The conductivity of the semiconductor is increased with the increase in temperature. This is in contrast to the conductors, where thermal conductivity decreases if you increase the temperature of the conductor due to increase in phonons or thermal vibrations of the atoms. However, in semiconductors, if you increase the temperature, you get more number of free electrons, so more conductivity. The most common examples which we study are silicon and germanium, which belongs to group 4. Both have 4 electrons in their outermost shell. So mostly these materials form covalent bonds due to the existence of 4 electrons and 4 vacant spaces in their outermost shell. So they need 4 electrons to complete their octet. So they share their 4 electrons with the other atom which also have 4 electrons to complete their octet using covalent bond. The energy band of the semiconductor is very similar to that of insulator. However, the only difference is the width of the energy band. So width is very large in insulator, whereas semiconductors have narrow forbidden energy gap. So in semiconductor, band gap is narrow, which allow considerable electron concentration in the conduction band at room temperature. So due to the presence of narrow band gap, at room temperature, many electrons achieve sufficient energy to jump from valence band to the conduction. The band gap of silicon and germanium is respectively 0.76 and 1.2 electron volt. This is 1.2 electron volt for silicon and 0.76 for the germanium, respectively. So the band gap of silicon is wider as compared to that of germanium. This is due to the distance of outermost shell electrons from the nucleus. So it means that electrons of silicon are more tightly bound with the nucleus as compared to that of the germanium. So if you see the electronic configuration of both of silicon and germanium, so germanium has 32 atomic number. So it has 32 electronic states which can be configured like this as presented over there. And silicon have 14 atomic numbers, so it has 14 atomic states which can be configured like this: 1s2, 2s2, 2p6, 3s2, 3p2. In both the cases, you see that the outermost fourth shell of germanium has 2 electrons in s state and 2 electrons in p state. So To complete its octet, it needs 4 electrons. Similarly, if you see silicon, there are the 2 electrons in 3s and 2 electrons exist in 3p. So to complete its p suborbital, it requires 4 more electrons. So this is the bonding configurations of various germanium atoms combined together, bound together with the help of covalent bond, which are sharing their electrons, which are making a pair of electron by sharing its own electron with the neighbor atom. So here you can see that this is central germanium atom having 4 electrons, and all these electrons which are existing in the neighbors also have 4 electrons. So each germanium share one of its electron with the neighboring germanium atom. So this germanium combined with this to increase its electron by 1, combined with its this atom to increase its electron by 1, and with this. So here you get 3, and if you combine it with this atom, then you get 4 electrons. So it have its own 4, and it have 4 due to the sharing with the 4 of its neighboring atoms. So this is how the covalent bond forms between the germanium atoms, which is a very popular semiconductor, which belongs to group 4. So it comes from the group carbon, silicon, germanium, and so on. All these have 4 electrons in their outermost shell. The concept of hole. So when what is hole? We want to understand the basic why this concept appears. So when electron move from valence band to the conduction band, it leaves behind a vacant electronic space. This vacant space of electron, this vacancy which is left by the electron, this unfilled electronic state is called hole. It is denoting the absence of negatively charged electron. So when electron combine with the hole, the charge will be annihilated. So it is considered to be a positive particle, having all the properties similar to that of electron, but with opposite charge. So holes are treated as positive particles. So for our understanding and for our easiness or convenience, a hole is considered to be an active particle just like an electron in the conduction band. So holes generally exist in the valence band. So holes are considered as active particle as we consider the electrons. So sometimes in some cases we consider holes as a charge carrier, and in some cases we consider electron as a charge carrier. So both are considered as active particle as far as semiconductor materials are concerned. Intrinsic semiconductors. Pure semiconductor is called intrinsic semiconductor, which have no impurity inside it. So there is nothing which is added to the added as impurity in the pure semiconductor, like a pure silicon, pure germanium, right? In which free holes and electrons are created only due to thermal excitation. So there is no reason to have free electrons if there is no thermal excitation. So charge carrier created are known as intrinsic charge carrier due to their class. The conductivity is also known as intrinsic conductivity of semiconductors. The concentration of hole in the valence band is same as that of electron in the conduction band because the hole formed due to the excitation of electrons from the valence band which goes up to the conduction band. So that is the reason that the concentration of electron is same as that of the hole. Electrons which are in the conduction band and holes which created due to the absence of electron in the valence band, which jumps from valence band to the conduction band. So common examples of intrinsic semiconductors are silicon and germanium. Extrinsic semiconductors. Oh, we have a problem with the pure semiconductors that at room temperature, very few electrons have sufficient energy to jump from valence band to the conduction band. So we have a very small number of electrons present in the conduction band, which are taking part in the conductivity process. So due to very small number of electrons which are present, the conductivity of a pure semiconductor will be very low. To overcome this problem, we have to add some impurity atoms so that the impurity atom can cause an increase in the number of free electrons which are present in the conduction band of the semiconductor. So sometime to increase the conductivity of a semiconductor, we add a small amount of impurity to a pure or intrinsic semiconductor. The newly formed semiconductor, which has some impurity inside it, to increase a specific conductivity, this impure semiconductor is called extrinsic semiconductor. So if a semiconductor exists in its pure form, it is called intrinsic semiconductor. And if you add some impurity in an intrinsic semiconductor, then it is called extrinsic semiconductor. So this impure semiconductor is called doped or extrinsic semiconductor. So the process of adding impurity is basically called doping. So generally we do doping of the pure semiconductor to increase their conductivity. So the impurity atom here is called dopant, and the process is called doping. Now, from where the dopant comes? So dopants generally comes from group 3 or group 5 elements. The elements of group 3 which have 3 electrons in their outermost shells, and elements of group 5 which have 5 electrons in their outermost shell. So the first class have a deficiency of 5 electrons to complete their octet, and second class have deficiency of 3 electrons to complete their octet. So depending on the type of element added, the intrinsic or the extrinsic semiconductors are classified into 2 categories. One is called N-type and the other is called P-type semiconductor. So it depends that which element or which elemental impurity is added into the pure silicon or pure germanium, so which results into the 2 categories. One is N-type semiconductor and the other is P-type semiconductor. So first we discuss donors or N-type semiconductor. So when an atom from group 5 element is doped in an intrinsic semiconductor. So you know that each intrinsic semiconductor like germanium or silicon has 4 electrons in its outermost shell, and the impurity atom has 5 electrons in its outermost shell. So impurity atoms share 4 of its electrons with 4 of its neighbors, because each germanium atom can maximum accommodate 4 electrons. So one of the electrons of the group 5 element is free. It basically lies near the conduction band. The energy of the impurity atom is larger as compared to that of the host atom. So that's why the free electron existing over there lies in the forbidden energy gap and create extra energy states. So this electron lies near the conduction band, so very small amount of energy can excite this electron and put it off from its energy level so that it can go to the conduction band. and conduction starts. So there is an extra electron added to our semiconductor. So this is how, if you add many impurity atoms, so you can have many free electrons which are generated in addition to the thermally generated electrons. So due to the presence of this extra electron as a carrier, these doped semiconductors are called N-type. They are negatively charged, so they are called N-type semiconductors. So they have negative charge carriers. So the conductivity will be due to the flow of electrons which have negative charge. So that's why they are called N-type semiconductor. So here the extra electron is provided by the dopant. So these atoms which provide extra electrons are called donor atoms. And the example of group 5 element can be antimony, arsenic, and phosphorus, which are commonly used as dopants to form N-type semiconductors. So things are very clear. What we have done, we have added impurity from group 5, which have 5 electrons, to the silicon or germanium, which is in its pure form. When you add impurity, 4 of the electron of the impurity atoms form covalent bond with 4 germanium atoms, and 1 electron of the impurity atom left unpaired. So this unpaired electron is basically create an extra energy state. This exists between valence and conduction band. So this extra energy state change the Fermi level basically. So now very small amount of energy is required to eject this atom from its energy state and put it into the conduction band. So what is in the majority over there? So we have electrons in the majority over there. Some of the electrons come due to thermal agitation from the valence band, and some come from the impurity atoms. So overall, the number of electrons in our semiconductor increases as there is an excess of electrons, as their conductivity is due to negative electrons. So that's why they are called N-type semiconductors. Now we discuss acceptors or P-type semiconductors. So this is the other class of extrinsic semiconductor. When atoms from group 3 element is doped in an intrinsic semiconductor. So atoms of group 3 have 3 electrons in their outermost shell. The examples can be gallium, indium, boron, and so on. So they have 3 electrons. So when they combine with the germanium, 3 of electrons of the gallium or indium or boron, which whatever the impurity is, formed covalent bond with 3 of the germanium atoms. And it's one of the state is still left unoccupied. So it has an extra hole. It is still unpaired because it has 3 electrons. So now it has 7 electrons in its outermost shell. So there is still a deficiency of an electron to complete its octet. So basically, these are the materials which accept electrons from the germanium. So these atoms are called, these impurities are called acceptor atoms, which accept electrons from the germanium or from the silicon. Therefore, they are called acceptor atoms. And due to the presence of extra holes as a carrier, the doped semiconductors are called, holes carry positive charge, so they are called P-type semiconductors. So the majority charge carriers by which the conduction will occur in a semiconductor are holes in case of P-type semiconductor. So they are called P-type semiconductor, and the majority carriers are electron in case of N-type semiconductor. So in both the cases, you can clearly imagine that when number of electron increase, number of holes decrease, and when there are increase in number of holes, then there is a decrease in number of electrons in the valence band. So when holes are majority carriers, electrons are minority carriers, and when electrons are majority carriers, then holes would be the minority carriers. Now, you can ask a question that how the conduction can occur through holes, because holes are the positive ion atoms which lose its electron. So basically, the conduction through the holes occur when a nearby electron left its atom and combined with the nearby hole. So the original hole is filled and a new hole is created, and so on. This process will continue. So holes basically shift, not drift. So shift from one position to the other position. So in P-type semiconductor, the conduction is due to the presence of holes, and the conduction due to the presence of hole, the motion of hole can be considered as motion of electrons in the opposite direction. So these are the 2 points we should have to be remembered. We should have to note that neither P-type nor N-type semiconductors have any charge. Both are neutral. This is a common mistake most of the students have when asked the question, what is the charge on N-type semiconductor, what is the charge on P-type semiconductor? N-type has negative charge or P-type has positive charge? No. Both N-type and P-type semiconductors are neutral. The reason is obvious. The reason is very simple. Because you are combining a neutral germanium crystal with a neutral atom from group 3 or from group 5. So two neutral groups combined to form a neutral crystal. So the reason is very simple. So electrons are in the conduction band. They are with their crystals. So they are not going anywhere. So there is no charge. So there is no free ion over there. So they have the charge carriers. But overall, if you check the neutrality of this group, both P-type and N-type semiconductors have no charge. They are neutral. And also note that if a pure semiconductor is doped with acceptor atoms, holes increases and number of electrons decrease. Hence, holes are majority carriers in P-type semiconductor and vice versa, and electrons are majority carriers in N-type semiconductor. So this is our today's discussion. This is the basic introduction about semiconductors. Hopefully you all understand it. Thank you very much for your interest.